Good morning, everyone. So welcome after cookie time to our seminar. It's my pleasure to introduce Professor Yontan Tan, who is spending quite some time in Virginia, right, in the United States, but also occasionally in Switzerland. Sweden, sorry. Yeah, sure. I mean, Sweden, Switzerland. Yeah, so Jonathan is focusing on massive stars, but in particular young massive stars. So those that are still in the formation process or have just formed. And he will talk today a lot about the formation of massive stars, where by massive stars we really mean like high mass stuff, 8 solar masses plus. Okay, so the floor is yours, Jonathan.
Thank you. Thank you, Andrew. Is this on? Yeah. Okay, now. Great. So thank you, Andrew. It's a pleasure to be here. My first time in Leuven, and well, Hugh showed me a nice bar last night, so we had some beers, and it was very, we had a nice warm welcome to the city, so thank you. So I'd like to tell you about massive star formation, and if I have time, we'll get to the very first massive stars, which I think are the seeds of supermassive black holes. And this is work we've been doing over many years with large numbers of students and postdocs and collaborators. I'll also highlight the Chalmers Astrophysics and Space Science Summer Program. It's for undergraduate and master's students. So if you're advising such students who are looking for research projects, the announcements normally come out in December with deadlines in February. So massive stars impact a wide range of astrophysics, and as we'll see from the very first objects in the universe, from primordial gas, metal-free gas, population 3 objects we think are massive stars, but just how massive we'll see. And then, of course, they influence galaxies by both physical and chemical feedback. They can impact the accretion of supermassive black holes. Even in our own galactic center, it's massive star winds that appear to be feeding a Sagittarius star. And of course, most stars form in clustered regions where massive star feedback is particularly important also for the evolution of protoplanetary disks. Now, the complexity arises, well, massive star formation, or star formation in general, but massive star formation in particular. We have gravity compressing material in the interstellar medium, but it's various, you can call them pressure forces, which are resisting collapse, and it's this interplay that makes things complicated. And these processes are operating over wide ranges of spatial and temporal scales. So I'm a theorist, and we start with analytic theory to describe some of these processes. We'll often have to take things to numerical simulations. I like telescopes, so I'll try whenever I can to go to a telescope and test some theoretical prediction, but more just because I like to go to the telescopes. So there are many open questions. GMC is a giant molecular cloud, so most of the molecular phase of the interstellar medium is organized in these 100,000 solar mass to million solar mass complexes. Whether they're gravitationally bound or not is debated, and their lifetimes are debated. They're not like stars. It's very hard to put a clock on a gas cloud. We'll see about that. So the initiation of star formation, is it because some kind of pressure support decays away inside a cloud? You can imagine thermal pressure cooling away, or turbulence decaying away, or magnetic fields diffusing away. Or is it some external influence that triggers a compression and instability? So the initial conditions of the clouds, either before they become star clusters, we call those clumps, protocluster clumps that fragment to star clusters, or the initial conditions of individual stars, we call those cores, how close are they to equilibrium? We're going to see then that the accretion mechanism for star formation, in particular for massive star formation, is debated between the so-called core accretion or competitive accretion merger type paradigms. The time scale is debated, how quickly star formation is happening relative to the free fall or dynamical time. And then why do we have the initial mass function, which has this particular shape, peaking at around just below a solar mass, and then this power law form? And what processes may limit the maximum mass, as well as all the multiplicity properties and clustering properties. So ultimately, for those trying to model galaxies, of course, often star formation cannot be resolved, and you need subgrid models for when is it initiated, is there a threshold, at what efficiency does it occur per free fall time, and so on. Okay, so massive stars, the work we have done essentially extends classical theories of core formation that Frank Hsu and others developed. So you have a self-gravitating gas core, there's some angular momentum, you have an accretion disk here, it's magnetized, the shearing disk spins up the magnetic fields, launches a disk wind or an X wind or both, which clears out bipolar cavities which open up and then remove much of the material. So with Chris McKee, back during the days of my PhD thesis, we worked, basically generalized this to include non-thermal forms of pressure, so both turbulence and magnetic fields could then allow more massive cores to, bigger than the gene's mass, to be present in this turbulent magnetized clump that we call here. And the boundary condition on a particular core at time zero when it forms is the pressure of this self-gravitating clump, which is related to the mass per unit area of the structure. So we have then basically this classical cartoon just put in here with a different boundary condition, and these red arrows represent this external pressure. So the pressure is basically Newton's G times the mass per unit area squared, sort of like the weight of an atmosphere in this structure. So the higher the surface density, the higher the pressure. That means the initial condition at a given mass needs to be more concentrated before it becomes unstable. And being more concentrated will then accrete at a higher accretion rate. So there are completely different theories out there still being discussed, which involve massive stars forming in a cluster environment. That cluster environment is crucial for the buildup of in fact, the whole mass function. So you have some stars that happen to be near the center of a globally collapsing protocluster clump, and they compete for mass, and the more massive ones sort of gain and gather more of the mass. But a crucial feature is they are surrounded by a cluster of low mass stars. And the nearest region in Orion is the source I here, we think, in Orion KL. And this has a very strange outflow, which doesn't look anything like the normal bipolar outflows we imagine in this scenario. It has this more spherical explosive bullets, which have a time scale of about 500 years, tracing back to the origin. So even and here's the latest James Webb images from this. So even in the nearest region of massive star formation, all of these different models are sort of debated. So it's still quite open. Anyway, our work has focused on seeing if we can develop take this turbulent core model and sort of go ahead and make predictions for various evolutionary stages from what we might call time zero, when the pre-stellar core is just present there, and then the later stages. But actually, if you think about it, how far back in time do we want, what does t equals 0 mean, even for the protocluster clump here? And so that's what I'd like to discuss now, a slight diversion here, because it relates to some of the work that's going on here in Leuven. So in fact, you might want to go back all the way to statistical properties of star formation on large scales in galaxies. And there's these famous Kennicutt-Schmidt relations that you may have heard about in sort of a foundational for extragalactic studies. The second, not the most famous Kennicutt relation, but the second one in his 1998 paper is the so-called dynamical Kennicutt-Schmidt relation that links the mass surface density of star formation rate, solar masses per year per kiloparsec squared, to the amount of gas per unit area in the disk divided by some measure of the dynamical time. And these are points from normal galaxies, centers of galaxies, and circumnuclear starburst disks. And this line is not a fit to the data, it's just a linear line here, which follows this relation here. Ultimately, it means that a fixed fraction of gas, total gas, turns into stars per orbit. And if you, these were disk averages, but if you later go to annually in galactic disks, it turns out to be about 4% of the total gas, so both the atomic and molecular, is turning into stars per orbit. And as a theorist, you think, well, that's really interesting. it's dimensionally correct. So, what kind of process could lead to that? So the work we did many years ago was to propose that it's actually shear-driven giant molecular cloud collisions are the rate-limiting step for star formation. So you'll often see in the literature, you've got to form the giant molecular clouds out of the atomic gas. I don't think that's the rate-limiting step, because we have a lot of gas in giant molecular clouds. 30–40% of the ISM is already in the GMCs. But rather, it's how do you make the denser clumps within them? So the very simple idea is that cloud collisions, which have been proposed for many years, but driven by shear, essentially a two-dimensional system, because these GMCs are as big as their scale height. That process may trigger star formation. So you can estimate the time scale for collision in a shearing disk. So you need to know the rotation curve. Most of our galaxies in a sort of flat rotation curve regime. Beta is the logarithmic derivative of the circular speed with radius here. So beta of 0 would be the flat regime. This would be the solid body regime. Of course, there's no shear here, so this process will only happen in the more flat regime. And people over the years, Gami and Ostreicher, for example, have worked out the cross sections for clouds interacting in this way. So you can then estimate a mean free path for a cloud to travel before it collides, so you can estimate a collision time, and I won't go through the details, but you can show that the collision time is a fraction of an orbital time, about 20% of a local orbital time, but modified to first order in beta in the following way. So if beta becomes close to unity, this would be much reduced here. Also, the times will be lengthened. So then the star formation rate per area is just the amount of gas you have per collision time, and you recover this dynamical Kennicutt-Schmidt relation, but modified by beta. So about 10 years later with Elizabeth Tasker, we put all of these clouds into big hydro simulations, in this case with ENSO AMR, and here we do cloud tracking to follow, basically confirm the collision rates that are about 10–20% of an orbit. What we've done with a CASTM student, Zaina at Virginia, this was one of her first year projects as a bachelor student, and Jiayi Sun, who's a Hubble fellow at Princeton, was basically look at all the ALMA FANGS data. So now we have high resolution resolved studies of sort of few hundred parsec resolution in a sample of about 50 nearby galactic disks, and look for this signature of the efficiency per orbit modified as a function of beta here. We're looking for, is there a decrease as you go to high beta, more solid body regime, and if there is a decrease, what is the index with the prediction of about 0.7. So as far as we can conclude here, the latest ALMA FANGS data confirm this prediction. This would be the opposite, for example, because normally think shear stabilizes gas. But here we have less shear and we have less star formation. So it's the effect that more shear is increasing the star formation efficiency per orbit, as you'd expect in the shear-driven model. So why is this important? What are the implications? Well, it's been known that GMCs have pro and retrograde rotation in the galaxy. This frequent collisions can explain that. How you maintain turbulence in molecular gas has been debated, but this process naturally injects galactic orbital energy into local cloud scales. If you're trying to measure are clouds bound or not, often clouds are colliding, so if you measure the ratio of gravitational to kinetic energy, the virial parameter, you may be confused. The issue of cloud lifetimes becomes reset. The cloud lifetime is reset every time you have a collision, which could be every 10–20% of an orbit, every 10–20 million years. Well, in the Gaia era, we see massive stars, OB associations. I don't know if it's a surprise, but they have very disturbed kinematics, quite irregular. So we think there's a very strong connection here, and this is one thing I want to talk to Andrew about, because this is a natural way to have disturbed kinematics at the point of star formation. And of course, this process we think could be the link between global galactic dynamics and sort of the parsec scales of star formation. Now, if you go to other regimes like dwarf galaxies or low surface brightness galaxies, late type disks, which have more solid body rotation, the prediction would be you have different efficiencies of star formation, perhaps different initial cluster mass functions, this could be a different way of, a cause of a different environmental effect of star formation. So because motivated by this, we've set up what we call the MC-Sim, a molecular cloud simulation project or group. So over the years, we've worked with a number of, these would be undergrads in green or red, PhD students, postdocs in blue, and faculty collaborators in black, to understand the kinds of structures you get in magnetized colliding clouds. And the kind of structures you can get are, shown here as an example. You can naturally produce dense gas. We personally think the ISM is magnetized at a dynamically important level, so magnetic fields are also important in regulating the structures. You naturally produce chains and sheets of dense gas which fragment, so you can have relatively isolated massive cores forming in these kinds of structures, also with disturbed kinematics. And as we've mentioned then, now connecting this, the kinematics of these cores to the kinds of kinematics that might be seen in OB associations would be very a nice thing to do. Typical collision speeds between clouds are order 10 kilometers a second, maybe 10, 20 kilometers a second. So that could naturally just be inherited by the stars that form. So, well, this is one of my reasons for being here, chatting with Andrew over the years. Andrew, of course, is leading the Milky Way mapper in Sloan 5, and one of the goals is to characterize the young massive stars, OB stars, and get their spatial and kinematic properties. And the first results are coming out from this program. So measuring, for example, velocity dispersions in the disk plane compared to vertically, or looking for the kind of kinematic signatures that might arise from GMC collision models is one area that I want to talk to Andrew about. Okay, on the other side of these simulations, we can zoom into individual cores. We've put in a lot of astrochemistry. In cold, dense gas, you have a lot of actually CO molecules freezing out. That changes the chemistry, raises up certain processes like deuteration. And in particular, certain species like nitrogen species become the ones that are good traces of cold, dense gas. So we've also started an infrared dark cloud group. Infrared dark clouds are the densest, darkest regions of giant molecular clouds. These are Spitzer mid-infrared images. So these are 3-color images from about 3 to 24 microns. And you see these dark shadows in here. These are the kinds of structures that are basically the densest parts of these giant molecular clouds. Whether or not they're created by cloud collisions is another matter. So over the years, we've worked on ways to get the mass structure by mid-infrared extinction mapping of these things, so we can get arc-second level maps in this way of very dense regions, and then follow up with the various telescopes. So ALMA, here I am, out of breath at 5,000 meters on the plateau here, but ALMA, of course, has transformed our ability to study at high resolution star-forming systems. So this is now a zoom into the main filamentary spine of that cloud here. Green is millimeter continuum, about 1.3 millimeter continuum dust emission that's tracing dense cores. Blue and red are blue and red shifted CO outflows, fast CO. So you see very ordered, very linear structures here. Here's a very isolated core, for example. And if you look closely, there even appears to be a preferential direction in certain regions of this that actually ends up being statistically significant, which may imply large-scale magnetic fields are having some influence from the large scale down to the small-scale orientation. Okay, so that's some of the early stages. Let's go up to the higher stages here. So the turbulent core model predicts the accretion rate that's going on to the star here. So it depends, as we've mentioned, on the mass surface density of the clump, or the pressure. So the higher this is in grams per cc here, the higher the accretion rate would be. And then this is a variable related to the initial core mass. Here we're assuming 50% efficiency. So this would be a 60 solar mass core forming a 30 solar mass star. And then there's an evolutionary variable as the current stellar mass grows up to the final value. Now, in numerical simulations over the years of cores with various properties, what's been found is the outcome depends a lot if the core is magnetized or not. So, for example, here they've only put in a 10 microgauss field. That's very similar to the diffuse ISM field, and the thing fragments like crazy. But if you put in, we'd say, more realistic field, more like closer to a milligauss, then there's just no fragmentation, and you get a single object forming. So that means, that's motivated us to go ahead and develop what we call sort of semi-analytic models of this cartoon here, of the infall envelope, the accretion disk, the outflows, and explore the parameter space, the pressure of the clump, the initial mass of the core, and then this is the evolutionary variable of the star here. And one key difference I should have said is, as we'll see, during the protostellar evolution of this object in the center here, for high mass stars, it can actually reach the main sequence, the zero-age main sequence structure, and become very hot, and thus ionize the gas in here. So you can have H2 regions within this outflow developing, and this, of course, will be quite different from low mass stars. So here's an example of the structure, the size of a protostar for different accretion rates or different pressure environments. From blue to black is 1 gram per cc is typical, 3 grams per cc in red. So that's the highest accretion rate. So the star starts big, there's a bit of deuterium burning, which maintains the structure. There's a luminosity wave, but eventually you become older than your local Kelvin-Helmholtz contraction time, and then you contract, and eventually your central temperature is enough to fuse hydrogen, and you could then keep accreting up the main sequence here. But you come down to the main sequence at a higher mass if you're accreting at a higher rate. So where exactly you come down here will depend on that accretion rate. So that determines then the size of the star and its surface temperature and the photon output that it's doing. So we put that into radiative transfer models, which are sort of shown here. So we have, again, this infall envelope solution, an accretion disk, a disk wind solution, and then we can make synthetic images at various angles. So this is the top outflow cavity is pointing towards you, so shorter wavelength light can scatter towards you more easily, that's why it's brighter. But as you go to longer wavelengths, it becomes more symmetric as you can peer through the dusty core. Then you build spectral energy distributions, and you have a grid of models which you can then fit to data. We've coupled chemistry to this infall envelope, so now we can make predictions for molecular species and ice species. Then we have MHD simulations of the process as well, just to have somewhat more realistic structures. Jan's staff led this program. And then, of course, we can do the same thing, radiative transfer, CO line emission. We can do, because there's a UV source, we can do a PDR, photodissociation region, modeling in the outflow. We can look at shock ionization for these ionized jets, and the polarized dust emission as well. So many things can be done here. So we have many predictions from such models. Now we need to go and test them. And that's our SOMA program. So when Sophia was flying, we would be using it quite a lot. So this is this kind of crazy facility of putting a 2.8 meter telescope in the back of a 747 here. They found an old 747 that could accommodate these changes. And these missions were, kind of complicated. They'd be planned almost like space missions. So here I am going to one of the briefings back in 2014. And of course, the telescope flies along in a certain direction. It's pointing out the side. It can go up and down like this, but it can't turn like this. So if you want to point at a certain object, you've got to fly in a certain direction. And then at some point, you've got to turn, look at something else, and you want to land again. So it's taking off from Palmdale. And, flight observation time about 8 hours, flight time about 9.5 hours here. It's quite complicated to organize all of this stuff. It was an expensive operation, but still, we were happy to use it. Now, it was an old plane when they sit you down in the 70s business class seats here, and you notice, well, all the panels are hanging off the walls, and it all looks a bit rickety. And there's a big hole in the back where the telescope is pointing out. So being a nervous flyer, I was a bit worried. And then I looked over, and there's this sort of $10 Walmart fan, blowing furiously on this very ancient-looking avionics, and I was told, don't touch that. You know, that's a critical part of the operation here. I don't know what's going to happen if you move that fan. Anyway, then you're up, and the door opens. You hope you're going to land. But of course, it sort of works, and then data is being collected. Although, you know, over the years it had a number of, you can imagine, teething issues. Anyway, and all that to get one source in one of those flight legs. So over the years, we did, in the end, about 40 or 50 regions. And of course, being high up in the atmosphere, 40,000 feet, you're above a lot of the water vapor, so you can do imaging at, you know, a range of wavelengths. We would use, in particular, the forecast imager up to about 40 microns. So the most recent SOMA paper just came out this year here. And you know, so we've developed basically automated methods to identify sources and fit their SEDs and derive the turbulent core accretion model parameters. Also, so with 3 main parameters, but we also have a viewing angle and an amount of foreground extinction, so 5 parameters in the end. So now we've about 100 sources characterized in these regions, and you can put them on diagrams like the current protostellar mass that's inferred from the SED versus this mass surface density of the clump. Krumholtz and McKee came up with a theory published in Nature that to form a high mass star, you needed to be to the right of this red line. And the idea was you need to have a high enough accretion rate, so you become have high enough accretion luminosity of a population of low mass stars around, that the temperature is raised up, that the gene's mass is high enough to form a high mass star. That was the idea. But it's obviously, you know, not, we have examples of high mass stars on both sides of the line here. And we would say, although, you know, I respect these guys, of course, very much, we can simply prevent the fragmentation with magnetic fields. So we don't need this thermal way to do it. So one thing we potentially notice is the most massive objects need to be in higher surface density regions. And one can come up with a theory for that to do with the star formation efficiency from a core as a function of how dense the clump or core environment is. So in high density regions, the core is harder to disrupt, whereas in low surface density regions, you know, you may disrupt it very easily. You may only form 10 or 20% of your mass into the star. So it's just more difficult to make 100 solar mass stars. Okay, so that was the SOPHIA program. Of course, we're following up with lots of different telescopes. So the radio in particular is used with the VLA to look for the ionized jets. Here I'm just making sure the VLA is working. It's, again, pretty scary at the edge there. And then, of course, ALMA, again, is being used. And then a lot of single-dish work for the chemistry, which in Virginia, West Virginia, we have this big, kind of crazy Green Bank telescope, 100-meter diameter dish here. If you go up to the top, it's, again, if you're afraid of heights, you've got to hang on for dear life, just like this guy at the top there. And let's see, then a range of other telescopes. LBT, Virginia is a partner in the LBT. I tried to hike in there in April, but I was turned away. I was booted out by the astronomers because I didn't plan my visit. So if you look, this is my only photograph. That is the LBT in the background. Anyway, next time. Anyway, some highlights of this sort of follow-up program. We have plenty of examples of what I'd call ordered massive star formation. So you have these pretty linear, pretty structured bipolar outflows that, again, very consistent with core accretion. We're looking for the number of companions. So here's an example where we've looked around the central object with ALMA, long baseline, and we're trying to find, you know, is there a cluster of other sources around? We don't find any in there down to some mass limit in the source. And this is a 40 solar mass star from the kinematics with a pretty ordered but wide angle bipolar outflow. Then in the LBT, we've used also with adaptive optics to also just try and count the number of low mass stars we can find in here. The outflow cavities help because they create low extinction regime. So the star is somewhere here, and we're trying to count low mass YSOs and supplement that with ALMA data to basically do this number of stars per parsec square diagram as a function of radius from the central star. And so I know you have some programs which are also very interesting in that regard. And then we will try and compare the different models of competitive accretion and core accretion in principle is a single star on its own, but of course it's in a protocluster clump. So as the cluster develops, you can naturally just create a cluster around, but it would have a different structure. Then sometimes we find binaries, we think forming by disk fragmentation. So this is an example, again, long baseline ALMA we published in 2019. We have kinematic evidence to constrain the orbit of the binary. And actually, hopefully later this year, we'll submit a paper which shows the motion of these two objects, which we're able to see now. Right, well, James Webb, of course, has come along, and we try and get some time when we can. So over the cycles, we're now at about 5 regions which have massive stars in here. Sam was an undergrad in Virginia in our summer program, so he's, I think, the first PI of a James Webb program. This is his galactic center SAG-C image. This is a massive protostar SAG-C here. It looks a little more complicated. Actually, one of the striking things here is the bracket alpha ionized gas with very linear filaments here. So we, again, think magnetic fields are important in the surroundings. Well, over the years, I would pop in to see James Webb. This is what the segments were lying around, and then later it's sort of coming together. And so I've been trying to follow it over the years. Well, this is something which I think is very nice. In the outer galaxy, Sharpless 284, it's about 4.5 kiloparsecs away. In the outer galaxy, the metallicity is about half solar. So it's quite similar to LMC-type metallicity. Here are various images. If you look at the 3.56 micron image, this is the protostar here. This, we think, is this outflow cone that is driving this big jet. So we have our SED models developed for half solar conditions, and we fit properties. We think it's about a 10 solar mass star here, and it's sort of driving this emission. So this blue color is excited H2 rho vibrational emission from obviously driven by this bipolar outflow. We just kind of got lucky that in the NIRCam field, we've got the tip of the spear here and the tip of the spear here happen to be in both, on the same image. So you can literally just do some simple geometry and see how symmetric is it in terms of orientation, direction, and length, and you can even allow what would be if this protostar was accelerating over 100,000 years. What kind of motion you might expect to hear. The bottom line is we think this is very ordered. It's very symmetric, which means that the accretion disk must have held its orientation steady for the full accretion history of this object. So, this is core accretion. I don't think you can argue against that. So, I have maybe 10 minutes, do I? 10, 15 minutes? So what I'm most excited about these days is actually the first stars, and so let me just give you a quick summary of what's going on here. And it relates to the supermassive black holes in the centers of galaxies. You can see the event horizons, but how do they form? And you may have heard James Webb has been finding lots of big black holes at high redshift, but of course even before James Webb, we knew of very massive quasars at redshift 7 or beyond 7, which when the universe is just a few 100 million years old. So it's a big question of how you could seed these black holes. So here in fact, are the sort of Sloan quasars that were found and characterized. So what a billion solar masses. What's shown here are Eddington-limited growth tracks. So if the accretion rate is capped at the Eddington rate by radiation pressure, then this would be the sort of maximum rate you could grow. And if you follow these back, then at redshift, even if you want to form your object at redshift 30, which is pretty out there, then your initial seed black hole would already be, more than 10,000 solar masses. So this has led we need a mechanism for some seeds to be in the supermassive regime, 10 to the 5 solar masses. So I'm not going to show you all the details here. I didn't think I'd have I don't have time. But the summary that we think is of the status here is that standard so-called population 3 metal-free star formation that we worked on also with McKee, because you contract to the main sequence at around 100 solar masses for the typical accretion rates, you ionize a lot, you evaporate your disks. It's very difficult to grow beyond 100 or a few hundred solar masses. So these are too light as seeds for black holes. Maybe you could merge stars up in dense star clusters, but the kinds of cluster densities you need are just not seen if we look locally. And also this would produce a huge amount of intermediate mass black holes, which are also not seen. Very, very limited evidence for intermediate mass black holes. Direct collapse you'll often hear as a term. This is from much more massive dark matter halos, so 10 to the 8 solar mass systems, where gas can cool by atomic cooling and maybe have high accretion rates to form a central object. But you have to stop molecular hydrogen from forming in these systems, and that requires external irradiation. And these conditions just seem to be very difficult to make in cosmic simulations. So the abundance of direct collapse systems seems to be orders of magnitude too low to explain all the supermassive black holes. Maybe enough to explain the known high redshift quasars, but if you want to make all black holes in a single mechanism, then you can't do it with direct collapse. So people are trying to give up on the Eddington limit, but actually the latest Sloan data measuring Eddington ratios doesn't find any evidence for super Eddington accretion. And so people are really getting desperate. You'll see papers now just quite happily talking about primordial black holes as the seeds, which are not astrophysical in that sense. Well, what we have proposed is a modification to standard POP3, which we call POP 3.1, which makes heavy seeds at high redshift. And the basic idea is this. You need some process to stop the normal protostellar evolution from contracting to the main sequence, where you become too hot, too many ionizing photons to accrete. And there is a proposed process. It involves dark matter, weakly interacting massive particle, dark matter, self-annihilation as an energy source in the first star. Now, when I first heard this, I thought it's crazy. I just don't want to, I told Aravind and Tarajan to please go away. Don't show me this Spolia, Fries, and Gondolo paper. But, he persisted, and we looked into it, and it turns out they're onto something. You see, the very first stars are forming co-located with a dark matter cusp. This is the only time in the universe you have a single massive star trying to form co-located with a peak in dark matter density. In fact, it creates the extra peak because it adiabatically contracts the potential inside about half a parsec where the baryons dominate. So because you have slow, gradual contraction in these systems, you raise up the dark matter density by orders of magnitude. And annihilation, of course, depends on density squared. So for standard WIMPs, which are needed for the cold dark matter and the relic density that we see, those cross-sections give you meaningful energy injection rates. So the WIMP is supposed to be its own antiparticle with a weak interaction. When they annihilate, we don't know exactly, but the standard view is maybe 1/3 of the time into neutrinos, which escape, 1/3 of the time into photons, which are trapped in the star, 1/3 of the time into electron-positron pairs, which are trapped. So those 2/3, the latter 2/3 of the energy is trapped and available to be an extra heat source in the star. So here are MESA models where you account for that with a finite initial reservoir, depending on the WIMP mass, and you can delay contraction to the main sequence, maybe as far as 1,000 solar masses here. But there is a solution where you could keep capturing more dark matter, because the star is surrounded by dark matter, and there is a solution where you just keep capturing. So now your structure is very different. The star is big and bloated. It's like a red supergiant. The hydrogen ionizing output is very low, And so you could continue to accrete most of the baryonic content of this dark matter mini-halo. The dark matter mini-halos are about 1 million solar masses. The baryonic content is about 100,000 solar masses. So this is a natural way to make supermassive objects at early times with this sort of dark matter-powered stars. And then later, well, you need more and more WIMPs to support, so you may run out at some point. There's a GR instability at around 100,000 solar masses. You may cross that. But there's a number of routes to make the supermassive seeds here. Well, so I don't have time to go into all the details, but the main prediction of this model before James Webb flew is that all black holes are in place by redshift 20. So you have an AGN-dominated era, and that's very much in line with then what James Webb was finding. There are many other predictions. So for example, these supermassive stars, before they become the black holes, they do ionize a lot of the universe. In fact, that process sets their abundance, because ionized metal-free gas ends up fragmenting because you boost the H2 cooling. But there's a prediction of flash ionization of the early universe at around redshift 2025, which for a while we thought, this is the scattering optical depth of the CMB, these were the Planck results. Our models were going a little bit too high here. But I don't know if you've seen in the last few months that there's a lot of discussion now. Maybe Planck was wrong. Maybe tau is not 0.06 but 0.1, because that would mean neutrino masses don't have to be negative. It also solves dynamical dark energy, the Hubble tension. So there's a number of things coming together. So we're actually very excited about this and happy to chat. It predicts all the black holes are born as single objects early on. The multiplicity is very low. Later, they merge as structure develops. So we have lots of things going on in this group here, which I don't have time to discuss. But basically, there are predictions for essentially everything, because this is the foundation for galaxies. Okay, so here's my summary. We're trying to develop a theory for how massive stars form. There are applications, of course, in our galaxy, but as we've seen at high redshift as well. The basic idea is there's non-thermal forms of pressure, especially magnetic fields and turbulence, which allow more massive cores to develop. But massive cores are rare. Massive stars are rare. Most of the cloud is not going to do this. So most of the time it will fragment to lower mass structures. So I personally think strong magnetic fields are needed to prevent the fragmentation, and then allow this initial condition to exist. We have plenty of examples observationally of pretty ordered massive star formation from just the geometry of their outflows. And we're developing quantitative, both analytic and numerical models to make predictions of everything from surface brightness profiles, SEDs, to the chemistry, the dynamics. Well, in the galaxy, we have a range of star-forming environments. I didn't discuss this so much, but within Sloan, for example, we're trying to use apogee and BOSS, now LVM, we hope, to characterize the young stars and the gas in these different regions, about 12 regions in the inner galaxy, outer galaxy, different evolutionary stages, to help characterize the stellar population. Now with Gaia and all the information it provides, as well as the accurate RVs, the kinematics of these O and B stars, I think, really carries a lot of information that will test these models. And then, well, somehow you have to make the supermassive black holes. I think the answer is making supermassive population 3 stars, which are very different because of dark matter annihilation, allowing them to grow. So I'll leave it there. Thank you.
Thanks, Jonathan, for the wonderful talk. Admittedly, looking at how much you work with observations, I think you should consider calling yourself like empirical theorist or something like that?
Well, I don't know how to open a FITS file, so.
I see. Yeah.
Thanks a lot. Very nice overview. I'm on John as well. I had a question actually from the last part, the supermassive stars, of course,
Yes.
which are super intriguing, and you outlined the dark matter annihilation scenario, right? Could you comment on also, because this of course, if I have understood it correctly, then I mean the key is to suppress the H2 cooling, right? So you need have some sort of atomic cooling halo, and then you could actually form them as well. There are other groups who work on that, and you can, if you just can destroy the H2, you basically end up with Lyman alpha cooling.
Exactly.
And you also end up with the supermassive objects, right? I think it's also Kava and those who work at least on the structure for myself. Could you comment on that as well, and what separates? And for me, for example, I work on the envelopes and potential outflows then from such. Would it be any difference between that scenario and the one that you outlined?
There are quite a lot of differences. So in this direct collapse from massive atomically cooled halos is very different from what we're saying is the POP 3.1 from mini halos, which are 10 to the 6 solar mass. But basically, the direct collapse scenario seems to be very, very rare. It doesn't seem to occur frequently enough to make all the supermassive black holes. The way it works is by irradiating this, you've got to have a metal-free, but massive halo that didn't yet form stars. It is prevented from forming H2 molecules, which are the main coolant. H2 forms in the gas phase because of free electrons through H- channel. So you've got to destroy the H2 coolant from surrounding sources. It's actually quite complicated mechanism, but if you could achieve it, then you'd have this contraction to a central object and have a very high accretion rate, which would then maybe allow this growth to supermassive scales. So that's how it works. But it just seems to be rare and difficult to achieve at scale in cosmological volumes.
Would there be any difference in the end state? Let's say you make a star, a supermassive star with the dark matter annihilation scenario, and then another one with the direct collapse scenario. Would you say that there would be any difference in how the stars appear? I mean, they would be super duper red supergiants, right?
Well, the star itself may be not so different in terms of its structure, but again, for the direct collapse, it relies on relatively high accretion rates. So maybe there's some difference in the structure, but that will be difficult to. The metallicity has been noted as some. So in our scenario, you make this heavy seed without much metals being produced, whereas in the other scenario, because you have this surrounding high UV from other star formation, you may make a lot of metals. That has been noted by a recent Myelino paper, saying they've measured the metallicity in one of these LR little red dots, and it's low.
If you allow just a follow-up on the same topic, because you mentioned at the end that you think that they could contribute to the reionization, to the ionization, right? But they're very, I was just wondering that, because they're red, right? So they're gonna emit enormously in the infrared, but not so much UV radiation. Or is it just, can you explain your thinking there a little bit?
Well, no, in this scenario, there would have to be a phase where they do eventually run out of WIMP support. So, as you go to higher and higher mass, you need more and more luminosity to support yourself, and you could basically just run out of this dark matter that you can capture. That's it's near the center of the mini halo. So, our preferred scenario is where they actually do run out of dark matter support. Then they do contract to the main sequence, and they live there for a few million years. The lifetime could well be extended by residual WIMP heating. And then, if you think, what is the hydrogen ionizing photon luminosity of a 10 to the 5 solar mass, a supermassive star in the ZAMS? It's about 10 to the 53 photons per second. So that's
even though they're very reddish on surface.
Well, no. If they contract to the ZAMS.
Okay. So you assume then that they remain blue.
They'd have to contract to the ZAMS to have this high photon output.
Sure.
But the numbers of supermassive black holes you need to make, you can actually get a self-consistent model where you have R-type expansion of an H2 region into the intergalactic medium at redshift 20 to 30. You make these one co-moving megaparsec H2 regions which sort of fill all of space. You have this flash ionization of the early universe, and that, those flash ionized regions would not make they would be 3.2s, not 3.1s, because they've been ionized. It's only the 3.1s which are undisturbed and make the black holes. Then you get an overall cosmic abundance of black holes, which is very compatible with what's known.
Okay. Yeah. Thanks. Brilliant.
Eitan, thank you so much for this very nice overview. I'm very interested also in the last part here, because especially the population of supermassive black hole binaries. I was wondering, is this also a possibility for the formation of like subparsec supermassive black hole binaries early on in the universe, or is that completely impossible with this model?
Our model makes predictions for this, yes. Let's see if I have backup slides here. Let's see if I can find them, backup slides. Where is the gravitational wave section? Let's see. I mean, the bottom line is we predict that the early black holes are born as single objects, and so you don't have many binaries. So that would be a key difference of our model. Maybe I'll just go to I talked about this last week here in a different. Yes, here we go. Well, the number of the dual AGN fraction is the metric, and that will depend on the lifetime of that phase. And we have this one parameter in our model is how isolated do we need to be this 3.1 source. This is improper distance, but our dual AGN fraction is very low early on. So if somebody was to say it's there are lots of dual AGN. At high redshift. So I talked to Xiaowei Fan, who's this well-known researcher in this field, high redshift quasars. I mean, he kind of developed that field. He has 30 redshift 7 and greater quasars with James Webb IFU data, and as he's told me, they all appear as single objects, for example. Whereas some models of black hole growth, I mean, I've seen simulations where there'd be hundreds of black holes coming together, and to make a 10 to the 9 solar mass object at redshift of 7. As far as we can see from the latest James Webb data, I don't think it's published yet, they're all singles.
Thanks.
We still have time for a couple of questions.
Coming back to the stellar scales,
yeah.
What about the binaries?
Well, disk fragmentation would make binaries.
But wouldn't you expect then that the companions are quite low mass in that case?
That I don't know. Let me see. We have found some massive binaries. I mean, there's this one that I mentioned briefly. Well, there's this idea of as the secondary grows, because it's further out, it will tend to gain more mass, and it will tend to equalize so there are processes discussed that will tend to equalize the mass of the binaries. But the fragmentation in the disk will depend on magnetization and temperature and disk. So there's quite a lot of uncertainty there in working out the fragmentation scale. So any new data you have on the masses that are found there would be great.
Yeah, so I mean, I love this paper. It's in most of my talks actually as an introduction, but also to outline a problem is that you put the scales there, right? The separation is a few hundreds of AU.
Yeah.
And most of the massive stars have a companion within 1 AU. And it's very hard dynamically to shrink an orbit from hundreds of AU to well within an AU. And within that 1 AU, the mass ratio distribution seems to be flat, so you have all sort of companions, but also quite massive companions. And I think no one has proposed a model that is able to produce those very short period systems.
Right, well, better get on it then. But it must be disk fragmentation, I guess, where else? We do have separate simulations on cluster scales looking at dynamically formed binaries, but they're not going to get into...
Dynamically, there's fundamental principles that tell you it's impossible, because if you try to harden them too much, you get ejected and you leave the central star, the central core of the cluster. And then you lose all the dynamical hardening possibilities, so you're stuck.
Well, is there a characteristic mass of these companions?
No, because the mass ratio distribution is flat. So, so you have masses from maybe 2, 3, 4 solar masses to companions that are 40, 50 solar masses.
Well, it'll have to be disk fragmentation and sort of dragged in by tides, in the disk.
More questions, comments?
You mentioned, that struck me, but you mentioned ordered star formation processes, and I was talking about binaries. Would a consequence or a prediction of these ordered star formation processes that the binary disk would all be aligned in the same direction? Because that we could test.
Right. Yeah, and we are trying to test it here, because there are disks around these components, and we're right now trying to test that. Of course, once you have a binary system, because of its orbit, there are processes that you can imagine changing the orientation. So, so it's not as simple as these kinds of, when I say ordered for more isolated systems, I'm talking about the outflow orientation. So local multiplicity is a way you could, of course, disrupt the orientation of things. But it's just, I showed some examples where we think systems have maintained their orientation of their outflows for the whole formation time. So then, because even this source now, G339, actually with the latest high-res ALMA data, we think this is a binary as well. So we know this is a binary, but its outflow is fairly ordered.
All right, we are at the hour. Let's thank Jonathan again. So Jonathan is around still today and tomorrow in the first half of the day at least. So find him and talk to him. And if you want something more organized, ask Uk.